And to find that things were wrong even with a hydrogen atom was a big shock. So it became the ambition of every theoretical physicist to understand this.
Imagine a world where energy flows endlessly, where power is derived from the very fabric of the universe itself. Welcome to the realm of zero-point energy, a captivating realm where the quantum vacuum holds secrets that could revolutionize our understanding of physics and transform the way we harness energy. We all come to today's episode of Exploring Zero-Point Energy. Deep within the quantum vacuum, a realm once considered empty, lies a wellspring of energy fluctuations that defy our traditional understanding of physics. This energy represents the lowest possible energy state of a physical system, where even at absolute zero temperature, the quantum vacuum vibrates with relentless activity. It challenges our fundamental notions of emptiness, offering a tantalizing glimpse into the hidden dynamics of the universe. In this episode, we delve into the historical development, scientific insights, experimental evidence, and potential applications of zero-point energy. Zero-point energy, a fundamental concept in quantum mechanics, challenges our traditional understanding of energy. To comprehend its significance, we must first delve into the foundations of quantum mechanics. At the quantum level, particles behave in ways that often defy our classical intuitions. Entire podcast series has been linked in the description below. Quantum mechanics describes the quantum vacuum, a vast expanse of space that appears empty but is teeming with energy fluctuations. These fluctuations give rise to what is known as zero-point energy. Unlike classical physics, where energy is expected to reach zero at absolute zero temperature, in the quantum realm, particles never truly come to rest. The concept arises from Heisenberg's uncertainty principle, which states that there is an inherent limit to the precision with which we can simultaneously measure certain pairs of physical quantities, such as position and momentum. This uncertainty gives rise to energy fluctuations within the quantum vacuum, even in the absence of external influences. These fluctuations create a sea of virtual particles and antiparticles that spontaneously pop in and out of existence, despite their transient nature. These virtual particles contribute to the total energy of the system, resulting in the zero-point energy. Remarkably, this energy is present even at absolute zero temperature, implying that the quantum vacuum is never truly devoid of activity. This sounds a lot like quantum foam. Yes.
As scientists began to delve into the mysteries of the quantum realm, they realized the profound implications of the same. The historical development of this concept unveils the efforts of brilliant minds who shaped our understanding of the quantum vacuum. From Max Planck's quantum theory to Albert Einstein's contributions to the field, the exploration of zero-point energy has been intertwined with the development of quantum field theory and our understanding of the quantum world. In the next segment, we will explore the journey of discovery and scientific insights that have brought us closer to comprehending its intricate nature. The exploration has a rich history that spans over a century. It all began with Max Planck's groundbreaking work on quantum theory in the early 20th century. Planck's discovery of quantized energy levels, where energy is emitted or absorbed in discrete units called quanta, laid the foundation for our understanding of the quantum realm. Albert Einstein further expanded on this concept with his theory of general relativity, which introduced the idea of spacetime curvature and its connection to energy. Einstein's equations revealed that even empty space, the vacuum, could possess energy and contribute to the overall dynamics of the universe. However, it was not until the development of quantum field theory in the mid-20th century that a comprehensive framework for understanding zero-point energy began to take shape. You can find a comprehensive video on the same in the I button and in the links in the description below. Quantum field theory merged quantum mechanics with special relativity and provided a powerful tool to describe the behavior of particles and fields in the quantum vacuum. The insights gained from QFT allowed physicists to understand that the zero-point energy arises from the infinite number of possible quantum fluctuations within the vacuum. These fluctuations give rise to virtual particle-antiparticle pairs that continually pop in and out of existence, contributing to the overall energy content of the system.
Furthermore, quantum field theory also explained the concept of vacuum polarization, where the presence of charged particles can induce a rearrangement of the vacuum's energy structure. This phenomenon has been experimentally confirmed and serves as a remarkable testament to the influence of zero-point energy. Theoretical frameworks and historical developments have laid a solid foundation for our understanding of zero-point energy. Now, let us explore the experimental evidence and observable quantum effects such as the Casimir Effect, Lamb shift, and vacuum polarization that substantiate the existence and impact of this intriguing phenomenon. The existence of zero-point energy is not merely a theoretical concept. It has been experimentally validated through various observations and quantum effects. These experiments provide tangible evidence of the influence and significance of zero-point energy in the physical world. One notable phenomenon that demonstrates the impact of zero-point energy is the Casimir Effect, proposed by Dutch physicist Hendrik Casimir in 1948. This effect arises from the interaction of fluctuating electromagnetic fields in a vacuum. When two parallel conducting plates are placed in close proximity, the space between them restricts the wavelengths of virtual particles, creating a difference in zero-point energy density. This energy imbalance leads to a measurable force that pushes the plates together. The Casimir effect has been experimentally observed and confirmed, providing strong evidence for the existence of zero-point energy. We already have an extensive coverage of this effect in our channel. It has been linked in the description below.
Another fascinating quantum effect linked to zero-point energy is the Lamb shift. Discovered by Willis Lamb and Robert Rutherford in 1947, the Lamb shift revealed a small but significant deviation in the energy levels of hydrogen atoms compared to what was predicted by classical theory.
Unchanged. Then in 1947, Willis Lamb and his grad student Robert Rutherford attempted to test the best version of quantum theory at the time, which was the Dirac equation. And they did this by measuring the energy levels in hydrogen more precisely than ever before. Now what they found did not match up with the theory. One of the energy levels was actually not one, but rather two very closely spaced energy levels, and this is known as the Lamb shift. They used microwaves to excite the electron between these two levels. So why were there two energy levels where there was supposed to be just one?
And Bethe then sat down and gave the first more or less adequate theory of the Lamb shift, just from a physical point of view. He understood that the reason why you had the Lamb shift was that the electron in the hydrogen atom was interacting with the Maxwell electromagnetic field in addition to interacting with the proton, so that the effect of the fluctuations in the Maxwell field were disturbing the electron while it was revolving around the proton, causing a slight change in the position of the orbits. And so that it was the back reaction of the electromagnetic field on the electron that Lamb had been measuring. And so
A quantum effect linked to zero-point energy is the Lamb shift. Discovered by Willis Lamb and Robert Rutherford in 1947, the Lamb shift revealed a small but significant deviation in the energy levels of hydrogen atoms compared to what was predicted by classical theory. This deviation was attributed to the interactions between the atom's electrons and the zero-point energy of the quantum vacuum. The Lamb shift not only verified the existence of zero-point energy but also highlighted its profound influence on the behavior of atomic systems. Make sure to subscribe to never miss any episode, especially one we are scheduling on this Lamb shift. Furthermore, the concept of vacuum polarization showcases the intricate connection between zero-point energy and the presence of charged particles. In the presence of electric fields, the vacuum undergoes a rearrangement of its energy structure, resulting in the creation of particle-antiparticle pairs. This phenomenon has been observed in experiments and plays a crucial role in phenomena like the spontaneous emission of light by excited atoms. The experimental evidence and quantum effects associated with zero-point energy provide a glimpse into the vast potential and implications of this intriguing phenomenon. From the Casimir effect to the Lamb shift and vacuum polarization, these observations illuminate the intricate relationship between the quantum vacuum and the physical world. But what is the point of theory if it can't be used to manipulate nature? This statement might feel rough to some, but that's the truth. We always try to manipulate nature using our knowledge of nature. Moving on. The discovery and understanding of zero-point energy have sparked immense interest due to its potential applications and transformative implications. While harnessing zero-point energy remains a formidable challenge, researchers and visionaries have begun exploring its possibilities in various fields. One area with significant potential is energy generation. Zero-point energy represents a vast reservoir of seemingly limitless energy that could potentially revolutionize the way we power our world. Imagine a future where we tap into the quantum vacuum to extract clean and abundant energy, free from traditional resource limitations. While the practical realization of this vision is still a distant prospect, scientists are actively investigating novel approaches and technologies to harness and utilize zero-point energy for sustainable energy generation. Moreover, this holds promise for advancements in propulsion systems. The ability to tap into this fundamental energy source could open doors to spacecraft propulsion that exceeds the limits of conventional methods. Concepts such as the warp drive or quantum vacuum propulsion have been proposed, leveraging the potential of zero-point energy to achieve faster than light travel. While highly speculative, these ideas demonstrate the profound impact zero-point energy could have on space exploration and interstellar travel. Beyond energy and propulsion, zero-point energy also raises intriguing questions about the nature of the universe and our understanding of reality. The existence of zero-point energy challenges our traditional notions of emptiness and raises fundamental questions about the fabric of spacetime. Its presence in the quantum vacuum suggests that the seemingly empty space is, in fact, filled with intricate dynamics and fluctuations. Exploring it provides insights into the nature of quantum fields, the dynamics of particles, and the potential interplay between the microscopic and macroscopic aspects of our universe. As we uncover the potential applications and profound implications of zero-point energy, it is important to acknowledge the controversies and debates surrounding this fascinating concept. The concept, despite its captivating potential, is not without its share of controversies and skepticism within the scientific community. Critics argue that the practical extraction and utilization of zero-point energy may be hindered by the immense challenges involved, such as the high energy densities and technical limitations that must be overcome. Additionally, the inherent complexities of quantum field theory and the fundamental nature of the quantum vacuum pose ongoing theoretical and experimental challenges.
However, despite the controversies, researchers and visionaries remain undeterred, continuing to explore the frontiers. Ongoing research efforts are focused on developing new experimental techniques, theoretical frameworks, and innovative technologies to better understand and harness this enigmatic energy source. Advances in materials science, nanotechnology, and quantum technologies offer potential pathways to unlock the true potential of zero-point energy in the future. Moreover, emerging theories such as stochastic electrodynamics and quantum gravity propose alternative explanations and models for zero-point energy, presenting fresh perspectives and potential breakthroughs in our quest to unravel its mystery. These theories aim to reconcile the macroscopic and microscopic aspects of the quantum vacuum and shed light on the nature and its implications.
But nothing would make sense if there was no quantum field theory. It is the fundamental basis of all the quantum effects that came after it. Click here to have a crisp understanding of QFT.